demonstrated by the TDDFT. They use a different theory for ground and first excited states. So there's no way you can have a proper coupling between them. This is exactly why Michael criticized DFT, TDDFT, because the TDDFT cannot describe the proper topology of this point section. Is simply because it's this. They are completely different theory. That's why there's no way they can do it. And this is exactly also Michael's point. It's most popular, of course. Everybody uses this. However, charge transfer state, we will, I'm not going to talk about the details, but double excitation is missing. It's a single excitation theory because we only collect linear response. Linear response is just a single excitation only. So the response space is just like the CI singles. You know the CI singles very well, right? So whenever you say CI singles is kind of a, well, the method that you don't want to use it unless you are really desperate, right? So the kind of method you have to use is something like CISD, right? Singles and doubles. At least you need the doubles to properly describe the excited states. However, TDDFT is a CI singles. And then incorrect topology. This was already mentioned by the Michael between S1 and S0. This is exactly very simple to understand because DFT, TDDFT combination. So you cannot get a proper topology. But because of there's no alternative in the linear response world, so this particular TDDFT is heavily utilized in various NAMD implementations. I mean, almost all NAMD implementation, they're using TDDFT. Even though it has a critical problem of S1 and S0 conical section, meaning that you can excite the molecule to the higher excited state, let's say S2 states. So you start with S2 states and then it goes to S1 state. That's fine because S2 and S1 are in the same response space. They are described by the TDDFT, so they probably well described. But as soon as you arrive at the S1 and S0, then there's a problem. So you don't know how to properly describe this particular situation. So you don't know whether you need to go to the ground or you need to stay in the S1 states. There's no way you can calculate that properly. So what they usually do is once you arrive at this particular conical section during NAMD, they simply stop the NAMD and then saying that, well, then we arrive at the end, so probably it goes to the ground. Well, that's not true. That's not correct. Okay. What are the alternatives to this? So let me summarize again. Linear response TDDFT. Your reference is at ground state singlet. Okay, then it can generate S1 states, S2 state, higher singlet, and it can also generate triplets. That's fine, but it cannot generate S0 states because your reference is S0. So there's no way you can do it. However, Martin Hedegordon and Anna Krylov in 2003, about more than something like 20 years ago, developed a very interesting linear response theory, spin flip TDDFT. That's what they call. And the idea is very different, but it's a similar idea. But they start with the triplet, high spin triplet. That's their reference. From this reference, the idea is very simple. Okay, so you have a T1 states is 2 alpha alpha. And then you flip one of them to beta. Well, is that what's really happening? No, it's not. But this is just a methodological excitation. Okay, just think about it that way. So you have alpha alpha, and you flip one of them as a beta, and then you excite to any orbitals. Okay, that's what it does. By doing that, your S ground state singlet can be part of response space. So now your ground state singlet is also in the same space. It's not response. Oh, sorry, it's not reference, but now it belongs to the same response space, so that there's perfect coupling among all of these singlets. So you do have a proper topology of S1 and S0 conical section too. So this looks great. And even the you can also generate T1. The same T1, you might think that, oh, why the same T1 can be generated here? Well, triplet has three states, three microstates, as we know. M sub S plus 1, minus 1, M sub S 0, right? So from this M sub S plus 1, you can generate M sub S 0 T1. So although they are the same T1, lowest triplet, M sub S is different. So even the reference T1 energy or T1 states can be properly coupled among other triplets. So looks great because all the states are now in the same response space. So there's no problem among the mixing different theory. So this looks wonderful. So then this is it was invented more than 20 years ago. So this is time that it should be most popular, right? It should be used more than linear response TDDFT, but then why we don't use it? So there's a big problem. Spin-flip TDDFT is wonderful. It overcomes many limitations of TDDFT. However, there is a problem. This is the problem. It has a severe spin contamination. This kind of spin contamination is different from the UHF spin contamination. That's a different types of spin contamination. This has to do with the missing responses. I will come back to this point. This is very important. So because of the spin contamination, what happens is if you calculate your states, right? And if you can check the S square value, which gives you spin states, right? Then sometimes a square value becomes 1. 1 means that it's a half-half mixture of singlet and triplet. What is that? It's, I don't know, half-half mixture of singlet triplet gives you very different energy, and it creates a lot of problems. It's not pure spin states. And if spin contamination is slight, then it's okay to use it. But if it's in the case of like the half-half mixture is a complete spin contamination, then simply we cannot use that particular states. That's the real problem of this. This is a wonderful theory. So not many people is using it. There are many criticisms about this theory. So simply because this problem, spin contamination. Well, okay. So there are people trying to improve this situation. Trying to remove spin contamination, and there are many attempts, but all these are the very complicated procedure, requires a lot more calculations, and many of them is too complex, then they don't have gradients. If you don't have gradient, you cannot optimize it. This is not usable. Okay, so that's a situation. Well, here Sungun and then we including Michael thought about this, and we overcome this problem. Okay, the spin contamination problem. Let me show you. I think this slide is the most complicated slide. So believe me, there's no more slide like this. Okay, so let's focus on. I think this is important. So the RHF is the reference of linear response TDDFT. This is what the linear response TDDFT uses as a reference. And from here, you excite one electron, okay? That's what the linear response TDDFT has. If you excite one electron, you cannot get the, here, do you see my pointer here? You cannot get doubly excited configuration here. I'm pointing doubly excited configuration. Do you see this? Can you? Okay. So this is exactly the configuration Michael included in his regs. This is necessary, but linear response theory cannot generate this doubly excited, because you know that this, as I told you, it's the CI singles theory. In the CI singles theory, there's no way you can excite 2 electrons, right? So therefore you cannot get this doubly excited ones. Well, let's look at this black triplet M-S +1 reference. This is, you have an alpha alpha, okay? You have an alpha alpha. Suppose the middle alpha, you flip it, okay? You flip into beta and excite to here, the one upper orbital, then you arrive here, right? So this is again single excitation. Single excitation, you get the double excitation-like configurations. It looks like it's a magic. To me, it's a magic. From this RHF reference, you cannot get this double excitation. But from this alpha reference, you can arrive at this. So your response space is a doubly excited configurations. This is really important, and this is very easy to get. Okay. Now, the problem of spin flip is that it can generate all of this, and it can generate the black responses here, all the blacks here, here. However, it cannot generate the red ones. Okay, for this red, I have a circle red, okay, this configuration. Let's think about this. How we can generate this configuration from this black reference? Well, you think about it. There's no way you can do it unless you do the double excitation, right? This is missing. The red ones are missing from the original spin flip TDDFT. Because of the red is missing, you cannot have a proper spin combination between the black and red. As a result, you would have a really severe spin contamination. This is the cause. This is the source of this. Well, how we can overcome this? The best way to overcome this is to generate this red. Let's generate it by single excitation. We thought about this a lot, but then we come up this. What about using beta reference in addition to black, the alpha? So if you start from this red reference and do the single flip, let's say to get that, you flip this guy, okay, the lowest beta orbital into alpha, and then you excite to this. Then you arrive here by single excitation. Of course, you have to flip it excited. So spin flip requires 2 processes. You first have to flip one alpha to beta or beta to alpha, and then do single excitation. Okay. By doing that, you can generate these red ones. Once you start recognize, you can generate the red ones, and now you have a proper spin combination between black and red, so that spin contamination problem is finally resolved by such a simple idea. That's exactly what we did, but it wasn't easy. It wasn't easy though, because idempotency problem. So if you have a single, linear response theory is a single reference theory. But what we are suggesting here is using 2 references, which means a multi-reference. As soon as you start using multi-reference, your density becomes a non-idempotent. Then you cannot drive the linear response theory at all. Okay, so your density has to be idempotent, even if you are using more than 1 references. That was a really challenging problem. And we thought about quite a lot, and and one point we come up an idea. What if we combine the 2 into a hypothetical single reference? That was really the crucial moment. We were able to overcome the major challenge of this, and be able to drive a new linear response theory. Anyway, I'm not going to talk about it, but soon probably he will. So let me show you. These are the results now. Okay, I'm not really, all the theory is gone now. So first question. Now we have a double excitation by doing single excitation. This is kind of strange word, right? Because we do have a double excitation, but it comes from single excitation, like these doubles. Do we really need it? That's the question, right? Do we really need, is this really important or not? That's really the question. So we did some tests. This is a linear chain of the, what is it? The polyation, okay? Then is a different size. The black one is the contribution of singles, and the red is the contribution of doubles. So you see that almost if you increase the size of the molecule, the contribution of the doubles increases up to 30%. If you go a little bit one more higher excited states, then the contribution of a double increases up to 50%. On the other hand, the linear response TDDFT does not have any double excitation configuration, that it only utilizes the singles and try to do whatever it can do. Well, this is, energy might be okay, but then the chemistry and physics behind this is completely not right, because we have to have a double character, but it's not there. So we absolutely need to have a double excitations, and our theory has a doubles. Oops. And also the conic intersection search, which you don't like to do because it looks complicated, but it's not, okay? So, well, it was complicated. With the spin flip TDDFT, if you try to search for the conical section between the ground and first excited, this is what happened. Okay, the red is the ground singlet and the blue is first excited. Initially, that's fine, but at some point, there's a gray line, which is a triplet. It's just in between the two. So at some point, optimizer doesn't know which one is which. So it keeps changing. Whether this is a singlet or triplet, doesn't know it, because the spin flip TDDFT does not tell you whether this is singlet states or triplet states. It simply gives you states. That's it. Well, so you can never converge. Okay. On the other hand, we completely remove triplet out of this figure, because of that combination, we completely separate singlet space and triplet space. So you calculate triplet space separately from singlet space, okay? So there's no chance of mixing of triplet. So just fine. So it will just find it. Okay. This is yet another case where average DFT fails, even at the minimum, even at the inside of a house, DFT fails, is when you have the diareticals, open shell cases. You know that DFT simply cannot use open shell cases, but our theory can, because we start with triplet and we generate the ground singlet, but the ground singlet is combination of multi configuration like this. It contains all of these configurations, so we could do it. But linear response TDFT is not possible. Again, the same thing here. Okay, this is again the H2 dissociation. We come back to H2, by the way. I started with the H2, but I ended up with H2. Well, my imagination is really limited to H2, I guess. But I just want to point out a couple of things. Again, the first graph is full CI here. So the black is your ground state surface, and the red is first excited, second excited, third excited. Third excited is a green, but the character of a third excited state is a double excitation character. You have to have a double excitation to properly describe this. That's what the full CI tells us. You see the MRSF has a proper and different functional, but the linear response simply doesn't have that state because it does not have a double excitations. Well, not only missing in this area, but also you see that eventually this double character will have avoided crossing with the S2 states, and then it comes back, it becomes S2. Double character goes down into second excited states in the stretched bond. Eventually, then it would have degeneracy with S1 states in the asymptotic limit here. So eventually, these two states has to have a degenerate energy. That's what the full CI is telling us. And MRSF is doing well. It's asymptotically correct. But linear response, these two states doesn't approach with each other. It's because at this point, the blue has to have a double character, but it doesn't. It only has a single character, so that therefore it's not describing the asymptotic region well. Okay. Okay, maybe this is almost the end. So let's compare Rex and MRSF one-to-one. So which one is better? Of course, Professor Flatov said that MRSF is better. Well, we say, well, I don't know. Okay, so let's think about the differences, okay? So first of all, number of configuration. Rex, few important ones. Ground doubles and doubly excited ones and open shell in the case of Rex 2.2. He knew that you just need a few of them to properly describe non-dynamic correlation, static correlation. You don't need any other, just those few. That's his idea. And then using those limited or just a few configurations. Well, we can think about this as in old days we have before the CAS-CF, there is MCSCF. Okay, CAS-CF is a complete active space, but the MCSCF is a multi-configuration SCF where you just pick the one you like. Okay, in the complete active space, it automatically generates all the necessary configurations. So you generate too much. There's lots of them. But MCSCF time, you just choose the one you like. This is almost like that, but almost like MCSCF, which is very selective configuration. As compared to that, MRSF generates a lot of them. Okay, all singles and lots of doubles, but it does not cover entire doubles. Okay, so in that regard, it's not like a CISD. It's like CIS with partial D. Okay, so it does not cover entirety, only partially. Though near the, we think that those D's are important D's. That's included. Well, there is also another issue here. I'm still doing right? So it's 44 minutes, still under an hour. Okay. There is a Dresden DFT by the Casida and the Miguel. They actually include all doubles because they thought that doubles are missing because the TDDFT has only singles, right? So they try to add all double excitations in their theory. But then what happened is that, you know, DFT functional is supposed to contain a lot of electron correlation already. And then you add all doubles. If you think about doubles, a lot more, okay? A lot more than you add too much electron correlation. We need to think about that. Because if you start with Hartree-Fock wave function, that's okay to adding all doubles. But if you start with DFT, which already have sufficient amount of electron correlation, then if you add all doubles, it could be too much. I think that's something we need to think about. So what I'm trying to say is that we need just a few of doubles, not all of doubles. Anyway, in terms of number of configurations, MRSF is a lot more. More configuration is better in a sense that it's more flexible in terms of the expansion-wise. However, RAGs, on the other hand, state-specific molecular orbital relaxation is possible, which means that you can optimize ground states. Also, you can optimize excited states orbitals. So orbital relaxation is really, really important to properly describe the state, the particular states. So his method can do the selective orbital relaxation of particular states. On the other hand, MRSF-TDDFT is not possible, okay? Because you just do the triplet orbital optimization, which is single reference orbital optimizations. Then you do the linear response. Using linear response, you got all the excited state states. And then there's no way you can specifically optimize particular state orbitals, because you always have to start with the reference. So you always have to use a reference orbitals. So there's no state-specific molecular relaxations. So, so in terms of the electron correlation-wise, which one is better? That's the question. Better orbital relaxation is better, or more the configurational expansion is better? What do you think? That's the question. That's the question. So MRSF has a more expansion, much larger expansion. But on the other hand, REX has a specific molecular orbital relaxation is possible. So advantage and disadvantage. Well, certainly REX molecular orbital relaxation of any states. But then because of, think about this, your expansion is limited. You only include a particular configuration. As a result, the number of possible states you can calculate is also limited by the number of expansion. Okay, if you have a two configuration, you can calculate 2 states, something like that. So if I'm wrong, please correct me, Michael. But on the other hand, the MRSF, you can calculate all states once you get the reference orbital. You can calculate all excited states. So there's an advantage and disadvantage, you can see. Well, another like Vladimir, Dr. Pomogaev is interested in spin-off coupling, for example. You know that you have done the spin-off coupling. In the games, we have a cassette-based spin-off coupling written by the Dmitry Fedorov. And if you want to use it, what you have to do is that for the occupied orbital, you have to transform the 2 states occupied orbital is the same, identical. You first have to make them identical. Then only the valence orbital can be changeable between different states. So which is very inconvenient if you have differently optimized orbitals for different states. I mean, I'm not talking about which that is better or not. I'm talking about the practical computational wise. If you have the same set of orbitals between different states, it's much easier to calculate spin-off coupling, kind of between states property calculation. So in that regard, MRSF is better. Of course, again, the more relaxation, meaning that all the states are variationally determined. It's the variational principle is strictly applied for any states. So your energy is guaranteed that it's higher than true energy. That's a very, very important variational principle tells us, right? But then MRSF is, the energy is not variational. It's good, but you don't know whether that energy is below or above the true energy. So there's an advantage and disadvantage. So this is one of the topics Michael and I've been thinking about, but then someone went to the Americas, so we couldn't pursue further. But what about combining the two theory? We use the Rex orbital, smallest possible set of Rex orbitals, and do the response theory on top of it. That would give us, we can enjoy both the orbital relaxation as well as long configurational expansion. So that way you can maybe have a much better way of quickly recover electron correlation. So this last sentence might be the one that we'd like to continue on. Okay, so okay, so this simply means that MRSF is much better than TDDFT. I'm not going to talk about the details. And so yeah, so further developments, okay, we want to do it. Okay, and yeah, in the spring we have a cherry blossom here, but this is not really fully, but we will have a much better spring this time. And thank you very much for all these people. And also, especially for the spin-off coupling, Toby Chan is helping us a lot, but we couldn't finish it. So we really want to continue on the spin-off coupling with these people. And thank you very much. Your question, please.
Actually, I have one important question.
Okay.
I'm going to discuss it a lot during my Monday talk.
Mm-hmm.
What about the accuracy? Actually, accuracy of the methods, it's just vital thing, actually.
Accuracy in terms of, I guess it depends on the particular property. Are you interested in excited states or?
Actually, unfortunately, both. Ground state and the.
It's unfortunate. It's unfortunate. It's unfortunate. Okay. All
right. We will discuss it on Monday because you think that optimization is just very understandable procedure for the quantum materials, and for the low dimensional lattices, it's not actually. And because of it, the accuracy of even optimization in the ground state is a vital thing, and actually for quantum materials. My first question: what is the accuracy for just structural optimization in terms of energy, of course?
Yeah, I think that our method is, so it depends on the system. So if the system is like a closed shell, like electron configuration, then it's almost like TDDFT.
Mm-hmm.
If it's open shell case, we are way much better, and TDDFT simply cannot do it for such a open shell cases. Open shell, you have a completely theoretical or intermediate open shell. There are many different situations we can think about. DFT, TDFT simply cannot applicable. I mean, not usable at all. So there's no alternative in terms of DFT wise. So this is the only theory. Rex and MRSF is the only theory for such open shell, even at minimum ground states. In terms of accuracy wise, it's all about the DFT. DFT accuracy depends on the exchange correlation functionals. And that's exactly we are experiencing again. And